Think about the world around us. We see trees, mountains, oceans, and stars. All these things, despite their differences, share something fundamental. They are all made of atoms. Atoms are the tiny building blocks of everything we see and touch. They are incredibly small, far too tiny to be seen with the naked eye. Imagine a single grain of sand. Now imagine something 1,000,000 times smaller than that grain. That's roughly the size of an atom. Despite their minuscule size, atoms are incredibly powerful. They combine and interact in countless ways to create the vast diversity of our universe. Understanding atoms is key to understanding how the universe works at its most fundamental level. From the smallest particles of dust to the largest stars in the cosmos, everything can be traced back to these tiny building blocks. In the next section, we'll journey inside an atom to explore its internal structure. Just like a bustling city, an atom has its own internal structure. This structure is both intricate and fascinating, with each component playing a crucial role in the atom's stability and behavior. Imagine the atom as a miniature universe, with its own set of rules and dynamics that govern its existence. At the center of this bustling city lies the nucleus, the atom's tiny and incredibly dense core. This nucleus is the heart of the atom, containing nearly all of its mass despite being just a fraction of the atom's total volume. It's like the downtown area of a city, where the most important buildings and institutions are located. The nucleus is like the city center, holding most of the atom's mass. This mass is due to the presence of protons and neutrons, which are packed tightly together in the nucleus. The density of the nucleus is astonishing, with a single teaspoon of nuclear material weighing billions of tons. Orbiting the nucleus are the electrons, much lighter particles that whiz around like cars on a busy highway. These electrons move at incredible speeds, creating a sort of electron cloud around the nucleus. This cloud is not random, but follows specific paths and regions, much like traffic lanes in a city. These electrons reside in specific regions called orbitals, similar to lanes on our highway. Each orbital can be thought of as a designated area where electrons are most likely to be found. These orbitals have different shapes and sizes depending on the energy levels of the electrons. Each orbital can hold a certain number of electrons. The first orbital, closest to the nucleus, can hold up to 2 electrons, while the next can hold up to 8, and so on. This arrangement is crucial for the chemical properties of the atom, as the distribution of electrons in these orbitals determines how the atom interacts with others. The nucleus itself is made up of even smaller particles called protons and neutrons. Protons and neutrons are collectively known as nucleons, and they are held together by a powerful force called the strong nuclear force, which is one of the fundamental forces of nature. Protons carry a positive electrical charge, while neutrons carry no charge at all. This positive charge of protons is balanced by the negative charge of electrons, ensuring that the atom as a whole is electrically neutral. Electrons, on the other hand, carry a negative charge. This negative charge is what allows electrons to be attracted to the positively charged protons in the nucleus, creating a stable atomic structure. The opposite charges of protons and electrons attract each other, much like magnets, keeping the atom held together. This electrostatic force is what prevents the electrons from flying off into space and keeps them in their designated orbitals around the nucleus. This delicate balance of particles and forces within the atom is what gives rise to the incredible diversity of elements we see in the universe. Each element is defined by the number of protons in its nucleus, known as the atomic number, which determines its position in the periodic table and its chemical properties. In the next section, we'll delve deeper into the forces that govern the interactions within an atom. We'll explore how these forces not only hold the atom together, but also influence the way atoms bond with each other to form molecules, leading to the vast array of substances that make up our world. We've explored the basic structure of an atom, but what keeps it all together? What are the invisible forces that ensure the stability and integrity of these tiny building blocks of matter? The answer lies in the fundamental forces of nature, specifically the electromagnetic force and the strong nuclear force. These forces are essential in maintaining the structure and stability of atoms, which in turn form the foundation of all matter in the universe. These forces act like invisible glue, holding the atom's components together. Without them, the atom would simply fall apart, and the universe as we know it would not exist. The electromagnetic force is responsible for the attraction between the positively charged protons in the nucleus and the negatively charged electrons orbiting around it. This force is a result of the electric charges of the protons and electrons, which create an attractive force that pulls them towards each other. This force is what keeps the electrons bound to the atom, preventing them from flying off into space. The balance between the attractive electromagnetic force and the centrifugal force of the orbiting electrons ensures that the electrons remain in their designated orbitals. The strong nuclear force is even more powerful than the electromagnetic force. It is the force that binds protons and neutrons together in the nucleus, overcoming the repulsive electromagnetic force between the positively charged protons. It acts as the glue within the nucleus, holding together the protons and neutrons despite their like charges. This force is incredibly strong but acts only over very short distances, typically within the confines of the nucleus. Without the strong nuclear force, the positively charged protons would repel each other, causing the nucleus to fly apart. This repulsion is due to the electromagnetic force, which would dominate in the absence of the strong nuclear force. These two forces, working in concert, maintain the stability of the atom. The electromagnetic force keeps the electrons in orbit around the nucleus, while the strong nuclear force ensures that the nucleus itself remains intact. They ensure that the nucleus remains intact, and the electrons stay in their designated orbitals. This delicate balance between the forces is what allows atoms to exist in a stable state, forming the basis for all matter. This delicate balance is crucial for the existence of atoms and, by extension, the existence of everything we see around us. From the smallest particles to the largest structures in the universe, the interplay of these fundamental forces shapes the very fabric of our reality. Understanding these forces not only helps us comprehend the nature of matter, but also opens the door to exploring the deeper mysteries of the universe. For centuries, scientists relied on classical physics to explain the behavior of the universe. This framework, developed by great minds like Isaac Newton, provided a comprehensive understanding of the physical world. It was a time when the laws of motion and gravity seemed to unlock the secrets of the cosmos. Classical physics, with its laws of motion and gravity, worked well for large, everyday objects. It explained why apples fall from trees, why planets orbit the sun, and why we stay grounded on Earth. These laws were intuitive and aligned with our everyday experiences. But when scientists began to study the tiny world of atoms, they encountered something truly perplexing. The behavior of these minuscule particles didn't fit into the neat equations of classical physics. It was as if the rules of the game changed entirely at this microscopic scale. Classical physics simply couldn't explain the strange behavior of atoms. The predictable, deterministic world of Newtonian mechanics gave way to a realm of unpredictability and mystery. Scientists were baffled, their classical tools proving inadequate for this new frontier. Enter quantum mechanics, a revolutionary new theory that emerged in the early 20th century. Pioneered by brilliant minds like Max Planck, Albert Einstein, and Niels Bohr, quantum mechanics sought to make sense of the atomic and subatomic world. It was a bold departure from the established norms. Quantum mechanics proposed a radically different way of understanding the universe, particularly at the atomic and subatomic levels. It introduced concepts that were not only counterintuitive, but also deeply unsettling to the classical physicist's mindset. It suggested that the deterministic laws of classical physics break down at these scales, replaced by a world governed by probabilities and uncertainties. Instead of precise predictions, quantum mechanics offered probabilities, a statistical approach to understanding nature. One of the most startling revelations of quantum mechanics was that particles like electrons could behave as both particles and waves, a concept known as wave-particle duality. This duality was a profound shift in our understanding of the nature of matter. Imagine a tiny ball also behaving like ripples on a pond. This analogy helps us grasp the bizarre nature of wave-particle duality, where particles can exhibit properties of both waves and particles depending on how we observe them. This duality challenged our fundamental understanding of matter and energy. It forced scientists to rethink the very fabric of reality, questioning long-held beliefs about the nature of the physical world. Quantum mechanics also introduced the idea that energy exists in discrete packets called quanta. This quantization of energy was a radical departure from the classical view, where energy was seen as continuous and smooth. Imagine a staircase instead of a ramp. In the quantum world, energy levels are like steps on a staircase, distinct and separate, rather than a continuous incline. You can only be on one step at a time, not in between. This discrete nature of energy levels was a groundbreaking concept that reshaped our understanding of atomic and subatomic processes. This challenged the classical view of energy as continuous and flowing. It introduced a new way of thinking about how energy is absorbed and emitted by atoms, leading to a deeper understanding of atomic structure and behavior. In the next section, we'll explore one of the most famous principles of quantum mechanics, Heisenberg's uncertainty principle. This principle further revolutionized our understanding of the quantum world, highlighting the inherent limitations in measuring certain properties of particles simultaneously. Stay tuned as we delve into the fascinating implications of this principle and its impact on modern physics.